So we can use linear approximation or the tangent line approximation to answer sort of questions about the behavior of a function. Idea is what we already know, right? So if I've got some function here at point A, x equals A, I can figure out now the tangent line, right? We know how to do that. And that gives me an approximation near A, like this is pretty good, right? Over here is a terrible approximation. But near the point, it's a pretty good approximation. And that is very useful, especially in terms of modeling, in terms of physics and stuff. You'll see that they will do that. Sometimes it makes calculations a lot easier to use a line than some function, sine, cosine, some crazy function, whatever. It's just a lot easier if you can use a line. And if you're close to the point, it is actually a pretty good approximation. So if I want to write this down sort of in a general sense, I'm going to take my function y equals f of x, right? So at the point A, right, we've got the value a f of a. This is the point, right? Here. A f of a. Now the tangent line has slope is going to be f prime of a. And then if I write down the equation for this line, it's going to be y minus f of a equals f prime of a x minus a, or y equals f of a plus f prime of ax minus a. So this is the line that is the linear approximation, and our book often calls this L of x. It's just the linear approximation to the function. So this is pretty easy to figure this out, right? You have to take the derivative, plug in the point. It's very easy. It's just the same thing we've been doing, right? It's finding the tangent line. So I'll do one or two like applications of this. The first is just find the linear approximation. So in order to give you some function, I chose cosine of 2x at the point A equals pi over 6. All right, let me get rid of this. I'm going to leave the equation up because we're going to use that. Right, so I'm just going to figure this out and plug this in. So this is really easy, right? F of pi over 6 is cosine of pi over 3, right? 2 times pi over 6. That's here, so that's 1/2. Okay. F primed of x is just minus 2 sine 2x. So F prime of your pi over 6 is minus 2 sine of pi over 3. That's going to be root 3 over 2. That's a 3, sorry guys. So I have negative root 3. So if I just plug this into my equation in the box, that's going to tell me that my linear approximation is going to be 1/2 plus or minus square root of 3 times x minus pi over 6. Okay, fine. So that's a good approximation near that point. Okay. Other thing you can do with this, which is sort of fun, is you can answer questions like estimate the value of something like this, 100.5, square root of 100.5. Okay, so this is a thing that people did back before they had calculators, right? So if you need to find this value, okay, how do you do it? Well, if you can use a linear approximation, it's much easier than somehow trying to compute this. So how are we going to do this? We're going to think about this. Notice that 100.5 is very close to 100, right? So we can think about our function here as being the square root of x, and consider the point A is going to be 100, right? So then we'll use the linearization around that point, and then you can plug in 100.5 into your line. And plugging in 100.5 into the line is a very easy way to compute something which otherwise, okay, how would you compute this weird square root, right? Of course, now you can just put in your calculator, so it sort of seems like, well, I'll just put in my calculator. But the calculator is computed too, right? So it's sort of interesting to historically understand why people were doing these sorts of things. And you can see why. I mean, it makes sense. So this would be 1/2 x, this, right? Well, 1/2 x to the negative 1/2. So we can write that way. All right, so now if I go back to this linearization, right, my point A is 100, so obviously f of A is just square root of 100, so that's 10. F primed of, 100, we'll call it 100. F primed of 100 is 1 over 2 root 100, so 120. And my linearization is going to then be 10 plus 1/20th of x minus 100, right? So that's just 5, right? So I end up with 10 plus 120x minus 5, or 5 plus 1 over 20x. So if I want to compute this number, because it's close, I can just compute, rather than the square root of it, I can just compute L of it, the linearization. So if I do that, I have 5 plus 1/20th times 100.5. Okay, so this is actually, since I did this is 10.025. Okay, and which makes sense, a reasonable sort of answer, right? Now, if I do go and stick in this square root of 100.5 into my calculator just to compare the difference between my approximation and a more accurate value, the accurate value that my calculator gives me is this. Okay? So this was very easy to compute, and you really didn't lose much. So it gives you, and that's of course because 0.5 is very close to 100. So this linearization is very good at this point, 100.5. Now, if I tried to put in something that was very far from the point 100, it would not be as good, of course, right? Because the linearization would be further away.